This is the Module 3 worksheet introducing the electrophilic aromatic substitution reaction and deriving its mechanism. In the 19th century, chemists discovered that bromine was stable in the presence of benzene, unlike other unsaturated hydrocarbons. Upon reacting at higher temperature, eventually a transformation occurred to give a low yield of bromobenzene. In the experimental details, the author mentions that pressure builds up, and if the pressure is not released, the reaction vessel can explode. By balancing the equation, we can realize that hydrogen bromide is a byproduct for this reaction. We know that hydrogen bromide is a gas, and it is also quite corrosive. If you don't want to wait for 8 days, you can mix bromine and benzene in a sealed tube and heat it up to 200 degrees, and in an hour and a half, an 83% yield of bromobenzene is produced based on the amount of bromine consumed. However, these are extreme conditions, and so most brominations are conducted by activating the electrophilicity of bromine, generally by adding a Lewis acid, although there are several types of strategies that have been demonstrated. In one of the methods that's described in the textbook, benzene is mixed with a small quantity of iron shavings, and bromine is slowly added dropwise. The solution is then heated to the reflux point of benzene. If this is conducted in an open vessel, the hydrogen bromide byproduct is released to the atmosphere. And after 4 hours, when the heating is stopped, we can isolate by distillation a reasonable yield of bromobenzene, which is separable from higher boiling byproducts of dibromination, which favor 1,4 isomer over the 1,2 isomer. Notice that the iron shavings are used in substoichiometric amounts, or catalytic amounts. The iron is actually a pre-catalyst, and a reaction of iron with bromine occurs, which is a redox reaction to give iron tribromide. And we can balance this equation. Iron tribromide is the actual catalyst for this reaction. Iron tribromide forms a Lewis acid Lewis base complex with bromine, which lowers the LUMO energy of the bromine to make it more reactive as an electrophile for the reaction with benzene as a nucleophile. We'll now write out some mechanistic claims that are consistent with the evidence that bromobenzene and hydrogen bromide are produced. The first claim that I will present is a mechanism that is described in the textbook. Benzene reacts with the bromine iron trichloride complex to form a carbon-bromine bond and a resonance-stabilized carbocation. The carbocation then forms bromobenzene, losing a proton, and reaction with the iron tetrabromide anion to form hydrogen bromide and regenerating iron tribromide as a catalyst. There is a second possible mechanistic claim, similar to the bromination of alkenes. In this case, the HOMO of benzene reacts with the LUMO of bromine iron tribromide complex, and a pair of electrons on the bromine comes back to form a three-membered bromonium ion. That bromonium ion can, in principle, open to give the resonance-stabilized carbocation, or there can be some other mechanism of elimination of hydrogen to give bromobenzene, HBr, and iron tribromide. In the next video, we'll explore which of these two mechanisms better fits the evidence.